Hello, my name is Marta Nuñez Garcia, and in this presentation I'm going to describe our method for automatic multiplanar CT reformatting from trans-axial into left ventricle short axis view. Multiplanar reformatting refers to the process of converting imaging data acquired in a certain plane into another plane. Basic standard cardiac imaging planes include planes that are oriented with respect to the major axis of the body, and planes that are oriented with respect to the heart, as illustrated here. CT images are acquired in transaxial orientation. However, cardiac pathologies are often evaluated using cardiac-oriented planes, and in particular, the left ventricle short axis view is often the diagnosis interpretation plane. Therefore, these interpretation planes and the corresponding reformatting must be computed very accurately. However, in clinical practice, raw transaxial images are reformatted into short axis view using manual landmarks, which is to varying degrees operator-dependent, time-consuming, and annoying. Image reformatting can be done by resampling the raw transaxial image along its subject-specific left ventricle short axis plane. Image resampling involves the image that is sampled given in coordinate system M, a resampling grid given in coordinate system M', the transformation T sub M' to M that maps points from the coordinate system M' to M, and an interpolator to get corresponding intensity values from the sampled image. We propose to compute the transformation that will map points from one view to the other one by using a few anatomical landmarks that are automatically computed from the corresponding left ventricle and right ventricle segmentations. So this is a schematic representation of the multiplanar reformatting into short axis view. For simplicity, we represent only surface models of the ventricles. On the left, it can be seen the initial image in transaxial view, and on the right, the corresponding image in standard short axis view. These are just two different views of the same thing, and these are just the three different views of the same thing. This is the subject-specific left ventricle short axis plane that will be positioned in the XY plane after the reformatting. If we clip this view, we can see that is the usual view of the set plane in short axis representation. We start by automatically segmenting the CT image using a deep learning-based method described in these two papers. Briefly, the method is based on the concatenation of two 3D unit networks, the first one using a low-resolution version of the initial data to locate the ventricles and crop the image accordingly. The second network is used to segment the ventricles from the corresponding high-resolution cropped images. The trained model was already available to us for this work, so we didn't have to train it, and we only use it for inference. The network outputs segmentation of the left ventricle endocardium, the endocardium, the wall that is shown here, and also the right ventricle epicardium. After image segmentation, triangular surface meshes are obtained from the masks using the Marching cubes algorithm. We use these meshes to compute the transformation T sub M' to M. This transformation is computed as the inverse of the rotation matrix R sub SAX that maps points from transaxial to short axis. This matrix considers three different rotations. R sub MV aligns the mitral valve plane, R sub S aligns the left ventricle septum, which is the relative position of the right ventricle with respect to the left ventricle, and the R sub LAX that aligns the left ventricle long axis. Finally, the rotation matrix R sub SAX is computed as the matrix multiplication of the three rotation matrices. All rotation matrices in this work are computed using the following processing. Given two unit vectors U sub 1 and U sub 2, a rotation matrix that aligns U sub 1 to U sub 2 can be computed using this equation here, where the parameters are easily computed from the unit vectors. To compute the different unit vectors, we proceed as follows. First, to align the mitral valve plane, we start by detecting the region corresponding to the mitral valve hole as the points belonging to the endocardial surface that are far from the left ventricle wall and also far from the right ventricle. This last condition is needed to avoid including points that correspond to the aorta hole, that is this region here, that, as you can see, has completely different normals with respect to the mitral valve region. We compute and average these normals and normalize the vector to have a unit vector. On the other hand, U sub 2 is defined as the mitral valve normal in a standard short axis view. In this case, it's just the vector 0, 0, minus 1. We apply the processing described on the left to compute the corresponding rotation matrix R sub NV. After multiplying the points in the mesh by the rotation matrix, we obtain these rotated meshes, where now the normals of the mitral valve region are aligned to the theoretical mitral valve plane. To align the septum, we proceed very similarly. Using again the distance to the right ventricle, we find the direction of a vector pointing from the right ventricle to the left ventricle. The unitary vector U sub 2 is now this one, is 1, 0, 0. And after computing R sub S and rotating the meshes accordingly, the right ventricle is now positioned according to its usual position in short axis view. The last alignment is the left ventricle long axis alignment. U sub 1 is now the unit vector pointing from the center of the mitral valve hole to the left ventricle apex. U sub 2 is this one, 0, 0, 1, and these are the final aligned meshes. This is an example where the three alignments are shown separately for illustrative purposes, but remember that we compute the rotation matrix R sub SAX as the multiplication of the three rotation matrices, and we compute the transformation all at once. So this is the initial trans-axial alignment. The first row shows the XY plane, and the second row shows the XZ plane. So with the first alignment, we align the mitral valve, so this part goes here. With the second alignment, we align the septum, so it's just the relative position of the right ventricle with respect to the left ventricle, so we align this to this. And with the last alignment, we align the left ventricle long axis. So we had this before, and after the alignment, we have this completely aligned along the Z axis. We use 25 images with available expert reformatting to short axis view. The average time was a bit less than 30 seconds, and we saw that our method replicates manual reformatting. We can see here some examples. So this is the initial original trans-axial view, and these are the reformated short axis views. This corresponds to the result corresponding to our method, and this is the manual reformatting. You can see that the results are very similar. This is another example. This is another example. And this is the last example that I will show today. To conclude, cardiac image interpretation relies on multiplanar reformatted images that are typically computed manually, being time-consuming and lacking reproducibility. We have presented a method to reformat raw trans-axial CT images to a standard short axis view that is automatic, fast, accurate, and reproducible. The origin, size, and resolution of the reformatted images that are defined by the resampling grid can be specified by the user, and this is useful in many applications that require a standardized representation of the data, such as to use a pre-trained network. Thank you very much.